Hi. Welcome to the technical overview of our work on threshold ECDSA. Here's the outline for this talk. I'm going to spend a good chunk of time going over the background and the prerequisites for understanding the components of our protocol. Then I will describe our protocol. I will specifically focus on the pre-signing and signing phases. Next, I will explain how to achieve accountability. And finally, I'll conclude by going over the security analysis of our scheme. So let's begin with some background and notation. By plus minus t, I denote the integer set from minus t to plus t. And I will also be using the following non-standard notation. Whenever an index disappears, it will denote summation. So if xi, kj, delta L become x, k, and delta, it means that we are summing over the relevant index. The convention also holds for double indices, so please look out for those. Next, let me define ECDSA. ECDSA is parameterized by a group generator order tuple associated with the underlying elliptic curve and a collision-resistant hash function h. The private key is simply a random element x in FQ, and the corresponding public key is g to the x in the group. ECDSA signatures come in the form of pairs R sigma, where R is a random nonce obtained by sampling a secret nonce K and computing the left coordinate on the elliptic curve of g to the K inverse. If you don't know what the left coordinate is, just think of it as a public deterministic function from the group to the field. The right-hand side of the signature, what I call sigma, is calculated as follows, where M is the hash of the message. Let's have a closer look at the formula and let's expand it. What I want you to take away from this formula is that in order to compute sigma, shares of sigma, it is enough to sample shares of k and then compute shares of k times x via pairwise multiplication between the k's and the x's. Of course, I'm cheating because I haven't told you how to compute R, but hopefully I'll remedy the situation later on. So finally, let me also display the verification algorithm for ECDSA. It's not really relevant for this talk, so let's move on to talking about the multiplication. So a standard way to perform multiplication is via Palier encryption, which I define next. Palier is a public key encryption scheme consisting of the following three tuple of algorithms. A key generation algorithm that returns an RSA modulus and its factors, corresponding to the public and secret key respectively. To encrypt a message, the sender computes 1 plus n to the power of the message, which is masked using a random nth power modulo n squared. Finally, here's the decryption formula. It's a bit funny looking and it's not really necessary for understanding this talk. So just keep in mind that it's easy to deduce m if you know the factorization. So as I said a moment ago, we use Palier to perform multiplication. And the reason it's particularly suited for this task is because Palier is additive homomorphic, meaning that we can calculate encryptions of additions by simply manipulating the corresponding ciphertexts. In particular, adding two plaintexts is like multiplying two ciphertexts, and raising to some power is equivalent to multiplying the plaintext by a known scalar. So next, let me illustrate how to perform multiplication using Palier. Suppose that A and B, each holding small a and small b, wish to compute shares of the product of their secret inputs. Again, the purpose of this exercise, as indicated also by the colors, is for the parties to obtain additive shares of the product of their inputs. Also assume that A is associated with some Palier key that they only know how to decrypt. So to obtain shares of the product, the parties proceed as follows. A encrypts his input under its own key and sends it to B. B uses the homomorphic properties of Palier to multiply the plaintext by B and then removes its share from the resulting value. Notice that the plaintext value of capital D is exactly A times B minus S2. Finally, A outputs the decryption of D and B outputs the value it chose in round in step 2. Okay, so this is how we do multiplication using Pallier. So now that we know how to do that, let me present the honest but curious version of the ECDSA signing protocol. So we assume that in a previous phase, the parties computed key shares of the ECDSA key pair, and each party is associated with a Pallier key that only they know how to decrypt. So the signing protocol begins with pairwise multiplication. Each PI sampled shares of the secret nonce K, as well as shares of an ephemeral value gamma, which will be used to compute the nonce. So in round 1, the parties initiate the multiplication between the Ks and the Xs, and between the Ks and the gammas, by sending encryptions of KI under their own key to all other parties. In the second round, the parties calculate the response to the multiplication by homomorphically evaluating Pallier and sending the relevant value to each party. So let chi ij and delta ij denote the prescribed output for each multiplication. And note that if you recall the index convention, delta is simply k times gamma, and chi is equal to k times x. In round 3, each party computes g to the gamma I. This is for the nonce calculation. And they send capital gamma I and delta I to all. Then, in round 4, each party has enough information to compute the signature nonce, because what's really happening here in the exponent is gamma times delta inverse. This is also known as the beaver trick, which is exactly K inverse. And they send the corresponding share of sigma to the other parties that depends on Ki, Chi, and the message. Finally, the output is computed by just summing up all the signature shares. So to summarize, in case the math was a bit fast, the protocol consists of 2 distinct pairwise multiplications. One for the nonce computation by inverting in the exponent using the beaver trick, and one to calculate shares of sigma. Good, so before I tell you how to compile the protocol for malicious security, let's discuss what kind of challenges we face. So during the multiplication, we are embedding values of FQ into Zn, which means that for certain plaintext values, the reduction modulo Q does not commute with the encryption process. What's more, this can be detected depending on whether the signature generation is successful or not. Specifically, equality holds if and only if the signature string verifies at the end of the protocol. So this may sound a bit academic, but it leads to the following attack. For suitable choices of gamma and beta, depending on whether the signature verifies or not, the adversary may deduce the value of a bit of the secret nonce, which in turn leads to all of these nonce attacks that you may have heard about. So how do we remedy this? So the solution is rather straightforward. Just make sure that the equality that I denoted by dagger always holds. One way to do this is by enforcing a range policy on all secret data. Specifically, secret values must be proven to lie in some interval much smaller than the Pallier modulus. Or, in slightly more formal terms, all statements must be accompanied by zero-knowledge proofs known as range proofs for relations like the one in the yellow box. So note that this is the template for malicious security that appears in Lindelnoff and Gennaro Goldfeder. But as you will see later on, we add a significant twist to the paradigm. Okay, so next I'm going to give you an example of a range proof. So before I do that, I need to tell you about Pedersen commitments. So at the core of the range proof lies a special commitment scheme that we call Ring Pedersen, which is also commonly known as Fujisaki Okamoto. The scheme is parameterized by an auxiliary RSA modulus n prime and 2 random quadratic residues in Zn prime. For the moment, you can think of these as being generated by a trusted party, but in the signing protocol later on, each verifier will generate its own auxiliary data for the commitment scheme. So as an aside, let me say that looking ahead to the fault attribution for accountability, this is going to make our life harder. Harder, rather. So, okay, that was an aside. So let's leave accountability for later. Okay, so to commit to some integer value x in a Pedersen fashion, we compute s to the power of x, and then we mask that value with the random power of t. To decommit, we simply reveal the secret and the randomizer. So what's nice about these Pedersen commitments is that they are binding over the integers rather than over some finite structure, which makes them particularly suited for proving statements about range. Okay, so now that I've told you about Pedersen commitments, let me describe the protocol for relation R. So it's a sigma protocol, 1, 2, 3 move. The prover claims that Pallier ciphertext C hides a small value which we denote by X. Further assume that the prover sent a Pedersen commitment to X to the verifier. So the protocol proceeds as follows. The prover samples a random Pallier ciphertext and a random Pedersen commitment hiding the same secret value alpha. The random secret is sampled in a slightly bigger range than X. This is for zero knowledge, and this bigger range is parameterized by epsilon. So you can ignore this epsilon if you like. It's not really necessary for understanding the talk. The prover sends ciphertext D and commitment Z to the verifier in step 1. In the second step, the verifier samples a challenge E and sends it to the prover. Now, depending on the challenge, the prover decrypts a specific combination of the ciphertexts and decommits a similar combination of the Pedersen commitments using the same secret W. Let me say that again. The prover's answer W is the plaintext value of the combination of the Pallier ciphertext and the decommitment of the same combination of the Pedersen commitment. Okay. So in the end, the verifier checks that the encryption and the commitment are valid and that W lies in a specific range. So the protocol may look a bit involved at first sight, but note that it's basically a Schnorr type sigma protocol, like the one for discrete log you may be familiar with. So to summarize, there are basically two things happening here. We are proving that ciphertext C hides the same secret as commitment Y, and the secret in commitment Y is small. The ciphertext and the commitment hide the same secret because we are opening the two combinations in round 3 using the same value. And the secret in Y is small thanks to the binding property of Pedersen. So next I'm going to present one way to compile the honest but curious protocol with range proofs, which corresponds to the Gennaro-Goldfeder protocol from 2018. So the compilation goes something like this. In round 1, we prove that Ki is small. In round 2, we prove that the Ds were computed as prescribed using small values. And finally, we also make sure that the nonce is well formed. So for the first call out, the authors use the range proof that I just showed you. For the second call out, they use slightly more elaborate range proofs. And for the last call out, to verify that the nonce is well formed, they devise a special purpose technique that incurs a few extra rounds of communication. So I won't discuss the technique in this talk because at this point, I would like to turn to our protocol. So we use the same template for malicious compilation, which I remind you goes something like this. So prove something about capital K, then prove something about the Ds, and check that the nonce is well formed. So starting from the bottom up, our first innovation is that we devise a special algebraic test for R. For this, we need to move a few things around and publish some auxiliary data. Namely, so a few things are going to move around. So namely, the parties send G to the gamma I in round 2, and in round 3, they publish Ki in the exponent of the product of the capital gammas, what I've denoted by capital delta I. And of course, they need to show that they use the right Ki. So at this point, in round 4, to verify that the nonce is well formed, it is enough to check that G to the small delta is equal to the product of the capital deltas. So the other innovation of our protocol is a bit more mysterious. So let me tell you what it is before I tell you why it's useful. In a nutshell, we instruct the parties to commit to the randomness, namely the betas, by encrypting those values under their own palier keys. And then we incorporate the resulting ciphertext into the range proofs by devising a slightly more elaborate range proofs. In other words, in the accompanying zero-knowledge proofs, the parties also show that the beta in D is the same as the beta in F. So at this moment, I would like to pause and try to explain what's happening. The reason we are adding all of these apparently superfluous ciphertexts to the protocol is because they enable extraction of the adversary's secrets in the security analysis. What's more, these secrets are extracted in an online fashion without rewinding the adversary. This allows us to argue that arbitrarily many concurrent signings can occur without compromising security, and all of the zero-knowledge proofs can be compiled with fiat shamir, thus avoiding the round complexity penalty of doing all the proofs in an interactive way. Good. So at the end of the execution, the parties are instructed to output the signature if it verifies. So modulo a few details. This is almost exactly what the protocol looks like. So next, let's look at accountability, and let's see how we deal with the faults during the signature generation. So if a range proof fails, then we have a smoking gun and the fault is attributed to the relevant party. However, for efficiency reasons, we take a slightly optimistic approach, and not all statements are proved to all parties. In other words, each party only verifies parts of the transcript. So if you recall, the range proofs are parameterized by auxiliary data that is generated by the verifier. So our proofs are only sound with respect to honest verifiers. So for our first protocol, the identification process incurs an n-squared overhead because it entails reproving the entire transcript to all parties GMW style in case of fault. So another drawback of GMW style accountability is that in the offline mode of operation, it requires that the party store the entire pre-signing transcript in memory in order to be able to identify the culprit. So GMW style accountability may be viewed as somewhat expensive and wasteful. For the second protocol, we do something much smarter, which is possible by slightly stretching out the pre-signing phase in terms of round complexity. So there are basically two things that can go wrong. Either the random nonce is malformed or the signature string does not verify. In the first case, since all the data for computing the nonce is independent of any long-term secrets, it's okay to simply open up the relevant palier ciphertext corresponding to the multiplication between K and gamma and verify in the clear which party sent the wrong value. The second case, when the signature string doesn't verify, is trickier because we can't really open the ciphertext corresponding to the multiplication between the K and the X because the underlying plaintexts leak the secret key. So let me tell you how we identify corrupted parties in this case. So the idea is to commit to the pre-signing data, the Ki and the Chi, in the exponent of the nonce by publishing what I've denoted here as J and Yj during the pre-signing, This incurs a small round complexity penalty. Then, once the message to be signed is known, we can check validity of the signature share in the exponent via the formula displayed at the bottom of the slide. The resulting identification process only incurs a linear complexity penalty in the number of parties, and it only requires storing 2 group elements per party in the non-interactive mode of operation. Good. So in the last part of my talk, I'm going to discuss the security analysis. Previous works on threshold ECDSA show security either via secure function evaluation of the ECDSA functionality or via standalone reduction to the assumed unforgeability of ECDSA. So we take a middle-of-the-road approach by showing that our protocols UC realize an ideal threshold signature functionality, which generically captures the essence of any threshold scheme. So as I will explain next, the proof boils down to showing that the UC simulation is indistinguishable from the real execution as long as the underlying traditional scheme is unforgeable. This new approach not only better captures our security goals, but it also allows us to argue security against adaptive adversaries, something that is not known for other protocols. So let me begin by defining the ideal threshold signature functionality in broad strokes. So when first invoked, the functionality requests a verification algorithm from the simulator. And already notice something unexpected about the functionality. It doesn't have a secret key. It doesn't have any secrets at all, to be honest. Then, for each signing, the simulator submits a message signature pair, and the functionality stores that pair together with a flag, depending on whether the signature verifies. Finally, every time the functionality is invoked to verify a message signature pair, the functionality returns the flag if it has record of that pair, and if not, if the message was never submitted and not all parties in the protocol are corrupted, then the functionality returns false. So at this moment, I want to pause and emphasize that the functionality will outright reject a message signature pair if it was never submitted. And this is how we formalize the traditional notion of unforgeability in the UC framework. So unless a message was signed by a quorum of parties in step 2, no efficient machine may calculate a valid signature. So to further drive the point through, notice that step 3 doesn't even use the verification algorithm. Unless, of course, all parties are corrupted, which is a pathological case. So the way I like to think about this functionality is as a repository of signature message pairs. Compared to functionalities that arise from a secure function evaluation, another peculiarity of TSIG, other than the fact that it has no secret, is that the outputs are submitted to the functionality from outside rather than computed internally, which means that the simulator has basically full control over the database. So these properties really work in our favor during the UC simulation because they make the simulation essentially trivial. So how does it go? So just run the key generation to obtain the public key and hand over the corresponding verification algorithm to the functionality. Then, after each signing execution, simply submit the message signature pair to the functionality. And finally, when the adversary decides to corrupt the party, just reveal the secret state to the adversary. So I just used a lot of words to say something really, really simple. Simulate the honest parties by simply playing exactly as the protocol prescribes. Good. At this point, you're probably wondering, where's the catch? It cannot be this simple, and it's not. The catch, as always, is in the fine print. So earlier, I made a big fuss about the verification process in the ideal threshold signature functionality. and how it captures the unforgeability. So because the simulator is simulating the adversary's view perfectly, the only way for the real and ideal distributions to be far apart is for the adversary to be able to forge signatures in the real protocol, which is utterly forbidden in the ideal functionality, as is highlighted from the stipulation on the slide. So it remains to show that the adversary can forge signatures. The way we do this is via reduction. We show that the adversary forges signatures in the protocol only by forging signatures of the underlying non-threshold signature scheme, in contradiction with its presumed security. Notice that because this is a reduction, as opposed to a UC distinguishing game, we are essentially taking the environment offline, which means that we can rewind the environment, which allows us to argue for adaptive security. So next let me explain how the reduction goes. So we define 3 separate experiments, and we show that if the adversary manages to forge signatures in the real protocol, then the adversary forges signatures in all 3 experiments. The last experiment will coincide with an existential forgery game for plain non-threshold ECDSA, which contradicts our base assumption. So the first experiment goes as follows. The simulator interacts with the adversary by first sampling an ECDSA key pair on its own and matching the public key of the session with the sampled key. Next, the simulator picks a party P star, which will be henceforth deemed as special. The special party is chosen afresh with every key refresh phase, and every time the adversary requests to corrupt the special party, the experiment is rewinded to the last key refresh. This technique of electing a special party allows us to handle adaptive adversaries, because we will argue that the adversary cannot guess this party all the time. So finally, the simulation is carried out by extracting the relevant secrets from the adversary instead of decrypting the special party's ciphertext. So in the paper, we show that as long as the zero knowledge proofs are sound, if the adversary forges the signatures in the protocol, then the adversary also forges signatures in experiment A. So the second experiment is almost identical to the first one, except that this time the simulator encrypts, what the simulator encrypts under the special party's palier key is different. Basically, instead of encrypting real secrets under the special party's palier key, the simulator encrypts zeros, by which I mean basically encrypts nonsense under the special party's keys. As you may probably guess, the next step in our argument is to say that if the adversary forges signatures in the first experiment, then, assuming that palier is semantically secure, it follows that the adversary forges signatures in the second experiment as well. Good. So finally, let's turn to the last experiment, which is what we're really interested in. On the surface, the last experiment will appear rather different than the first one. So let me give you the outline of the experiment C. So first, the simulator does not sample its own key pair, but rather requests a public key from an ECDSA oracle. So it doesn't know the corresponding secret key. Next, like in the previous experiments, the simulator chooses a special party and encrypts nonsense under its key. And for the simulation to be performed successfully, the simulator extracts the relevant secrets from the adversary, but also requests signatures from the ECDSA oracle. The simulator has to request signatures from the oracle because, contrary to the previous experiments, in experiment C, the simulator doesn't know the underlying secret key, and it must use the oracle's answers and the adversary's secrets to compute the special party's messages. From the adversary's point of view, experiments B and C are actually identical. And it follows that if the adversary forges signatures in experiment B, then the adversary forges signatures in experiment C also. And since the latter is the existential forgery game for non-threshold ECDSA, we arrive at a contradiction. So to summarize, we show that under suitable cryptographic assumptions, our protocol UC realizes in the random oracle model the ideal threshold signature functionality if and only if plain non-threshold ECDSA is unforgeable. So for the non-interactive mode of operation, we require a somewhat enhanced variant of unforgeability. And we provide evidence for this assumption, including a formal analysis in the generic group model. So to conclude, let me say that other than the random oracle model, we do not use any other heuristics in our implementation recommendation, such as exotic assumptions about extractability of proofs or something along those lines. We do not use any such assumptions. Good, so that was my talk. Thank you very much for listening.